Hi, my name is Marek Perkowski, and my collaborator on this paper is Kal Yu, a young teenager who works on programming and inventing some ideas. So the title of the paper is Binary, Multi-Valued, and Quantum Board and Computer Games to teach synthesis of classical and quantum logic circuits. Here you see the example of young teenager creating new quantum synthesis and quantum oracles. And I worked for many years with a group of teenagers from 12 to 19. These are usually children of professors and high-tech company engineers and managers like Intel or Tektronix. And they obtained many awards in national competitions, published many papers. Most of them are very good students. They are enthusiastic and hardworking. Most of them are Chinese or Indians by origin. We have 2 meetings a week for 2 hours, sometimes longer. And recently, we have this meeting by Zooms. But also students work at home, and they are permanently challenged to solve problems. This is my method, okay? So here you have the examples of some of those students that were building robots, programming robots with quantum Grover algorithm or other. They won several national competitions. They're developing new theories for circuit design, for quantum algorithms, and are playing games. Actually, young people like to play games very much, and I wanted to use this opportunity that there will be programming games and they will be solving games, learning about quantum and circuit ideas. On this slide, you see the rows are different types of logic circuits, and the columns are the methods that we are playing to solve those circuits. So we have Carnot maps, Markov charts, hypercubes, battleship games, shifting games, and games in Hilbert space. So the games that we will discuss are related to sum of product minimization, product of sum minimization, exclusive sum of products minimization, and disjoint sum of product minimizations. And we'll discuss problems such as product implicants, prime implicants, essential primes, symmetric functions, linear functions, unary functions, and other. Here is an example of simple game in which Alice, shown in red, and Bob, shown in blue, play to gain as many as possible finally covered minterms of this Carnot map. And as you see, this Carnot map has also don't cares. So Alice is playing the greedy strategy to cover as many minterms as possible, selecting here group BD. But this group, as you see, is redundant. It is useless because the whole function can be covered by essential primes shown here, here, and here. So Bob here is playing smarter strategy. He knows about essential primes, and he selects this prime. Then Alice responds with this, Bob responds with this, Alice responds with this. In the byproduct, they learned about essential primes, and Bob won 4-3 with Alice. This kind of games we call sequential games. Most of our games is sequential. Here you see the example of the Carnot map with 6 variables in which ones, zeros, and don't cares are randomly generated, and we can control the percentage of each. Here is another example, Carnot map with 7 variables. We can create Carnot map up to 8 variables, and then the game becomes quite sophisticated. And here is an example that the green was playing with this group, and then red responded with this group, taking this minterm over from green to red. The games to teach multi-valued logic have been also invented, like ternary input, binary output, ternary input, binary output, and we have the operations minimum, maximum. We can have the hybrid logic with binary output. We minimize by layers. Here is an example of the hypercube. We generalize the hypercube from binary to generalized. So this is a hypercube for 2 ternary variables, which is a Cartesian product of 0, 1, 2 with 0, 1, 2. And the Alice selects the first move, which is shown here. It is A01, B01. She covers 3 ones and 1 0. Min term 1 1 is flipped by her choice from 0 to 1. And then Bob selects this move, which is A12, B12, right? And as a result of his choice, the min term 1 1 is flipped back to 0. So ultimately, Alice covered 3 true min terms and Bob covered 3 true min terms. This is a draw. The result is 3-3. And the byproduct of this game is designing this circuit with the Toffoli gate binary here and ternary controlled Feynman here. The games to teach machine learning teach concepts like Occam razor, minimum cost design, Wapnick-Chervonenkins principles. Here is an example of the Carnot map with 8 variables and don't cares and ones and zeros. And here we see the neighborhoods for variables for rows and columns. And here is a Markant chart also showing the neighborhoods. And there is here group CD shown in Markant chart and group, this was CD. Sorry, this is CD and this was EF prime group, right? So as you see, for big number of variables, especially ternary, it is better to use Markant chart than Carnot map. It is easier to find the groups because there are some standard rules how to look for those groups. And we have also games to teach quantum concept like superposition, entanglement measurement. They are more advanced. Here is an example. So instead of using single moves, the players play like in multiverse, in many worlds at the same time. So it's a superposition. So at the beginning, R1 creates the superposition of these two. And the blue responds with this superposition. So now here we have a conflict because in case of measurement, R1 can measure this or this, and B2 can measure this or this. What will happen if the 0, 0, 1, 1 will be selected? Then there will be conflict between red and blue. And this conflict is solved like in the next slide. Ultimately, after resolving this conflict, I have the situation like here, after measurement, both of red and blue, and then they play again. Sometimes they especially create conflict. There's a new conflict. This conflict is resolved. As a result of resolving this conflict, blue has 3, red has 4, red 1, okay? So in this kind of games, either there is a supervisor who solves the conflict, or conflict is solved completely randomly by the measurement. Here is the explanation of resolving the conflict. First, red starts with superposed groups R1, 0, 0, 0, 0 plus 0, 0, 1, 1. Blue responds with superposed groups, as we discussed. Both red and blue make claims the cell, as we discussed. So now there is a conflict. Conflict is solved by measurement, okay? Assigning R1, 0, 0, 1, 1 to red, and B2, 1, 1, 1, X, which is ABC, to blue. And now red selects this, as you see here. He asks for conflict, and next conflict is here, because both of them claim this product group. There is a measurement. As a result, 0, 0, 0 is assigned to red, and 1, 1, X is assigned to blue, and this is the final situation, and later on, the next conflict is created, okay? So you see, this game teaches about entanglement, superposition, measurement. We have also games to teach quantum circuits, like ESOP for oracles and reversible permutative functions. Here is an example of logic battleship game. There are 2 players, like is a well-known battleship game. Here is some separation. So blue player doesn't see the ships here, and red player doesn't see the ships here. And as you see, the solution is this product group and this product group. This is the ESOP game. So when they overlap, they create 0. The same is here, right? And the red player shoots. He shoots, and the blue player tells 0, 1, or don't care. And the percent and the numbers and places of zeros, 1, and don't cares inside the selected groups are created randomly. So now, assuming this situation, let's analyze only the moves of the red player, but of course at the same time they play in term red, blue, red, blue. So let's say that after many shoots to 0, he shooted the final 0, and in the next his term, he shooted 1 here. Aha. So he knows that there must be somewhere the group of 4. What are the all possible groups of 4? This is either green or blue or red or black. 4 choices. So he guesses red. He is right. Okay. So now he knows that this group is already covered, but here is 0. Then there must be some another group that overlaps with this 0. So of course his guess is this group BD. He guesses here, but it is don't care. Then with assurance 100% or very close, he knows that this is 1. And he should BD, and he covered all mean terms, and this blue player tells honestly, you covered all my mean terms, right? Actually, if he knows that there's only 2 sheep products, then he knows that he's done. At the same time, the blue plays, okay? And the byproduct of this game is creating this quantum circuit in binary logic. And now I'll show you some interesting development permutation games for reversible logic. We know that permutative circuit with reversible for reversible logic, they have no ancilla bits, and this is decomposing big permutation to small permutations like here. So this permutation here is decomposed to small permutations shown here, right? And these small permutations are shown graphically on these bars. So in this case, we have 4 bars which are moving up and down, and the player can do only one move, but if he increases the number of correct mapping, he has additional move, okay? So these players move these lines up and down and observe in the window. If this window, you follow every possible input to output, if it is consistent with your permutation, you are done, and the last player won the game, okay? So now I'll just animate few situations, how we are animating this up and down motion. Ultimately, this is selected, and one of the player wins. Finally, conclusion. We invented many games to teach sum of product and similar problems, also games to teach machine learning, where we can take some real problem from benchmarks, and games to teach quantum circuits, both binary and multi-valued. Especially interesting are games for ESOP, but also games for permutations, and quantum games illustrate the concept of superposition, entanglement, and multiverse. But what is also for me very important, that in this bad time of pandemia, we are using Zoom with teenagers, and they have fun playing games, competing, and they are enthusiastic and active in this out of school difficult times. Thank you.